Okay, good. Let's start with the feedback sheets from yesterday. I think everyone had some or the other comment on our Hessian modification scheme. Looks like it generated a lot of interest. Again, one student, I don't know the name, is saying that, so remember we said we could take our matrix A and add tau times our identity matrix to it. And we said that that definitely pushes all the Gershgorin disks to the right half plane and therefore we are saved. The student says that we had a follow-up suggestion, I think, from you that why not modify only those disks which were going into the left half plane instead of modifying all the disks. And the student feels that that cannot be done. It would be possible only if A was in diagonal form. But that's not the case, right? The Gershgorin disk theorem said that you can find the center for any matrix. It need not be a diagonal matrix. Any dense matrix, the center is given by what? The diagonal element, that's the center, and the radius is coming from absolute value of the sum of the other elements. So, as long as I move all the disks to the right half plane, I don't have to move all of the disks, only those guys which have some spillover on the left half plane. It should work. So, whoever this is should give a little bit more of a reasoning. Is everyone convinced by that argument? That we need not move all the disks, we should just move those disks which are give the possibility of a negative eigenvalue. To save the modified Hessian from poor condition number, we make delta large, but if we make delta large, therefore the value of tau increases, right? So how can we solve both problems with the same solution? Obviously we cannot. This is classic engineering, right? It's a trade-off. If you try to make the condition number better, you are adding more, you are modifying the matrix more. So the deviation from the original problem is more, but you got a better condition number. So you cannot win in both situations. I think I clarified this by the end of the class, but the question is still here, that Gershgorin simply mentions that the eigenvalue lies somewhere in the disk, but where and what exactly it is, we don't know. Right, so this, where's my pen gone? Supposing this was this is the origin. So does this automatically imply that that we have a negative eigenvalue? No, right? Because the eigenvalue could be sitting here. So that's why Gershgorin is a very coarse tool. It's giving us a range. So an eigenvalue could be here, in which case we are in trouble. But to be on the safe side, what you could do is if you shift this over here to something like this, then there is no chance of a negative eigenvalue, right? That's what we are doing. But as the student is observing that we don't know exactly where this negative eigenvalue will be. So it is a bit of a overkill and the cost is very low. So that's the trade-off. If the Hessian is being modified, this is a good question, isn't it similar to the Quasi-Newton method where the Hessian is being approximated? In a sense, the philosophy is similar, right? That we don't, it's a little bit, the Newton method is of course more expensive because first you calculate the Hessian, then you find out whether or not it is positive definite. So you already paid the price. In Quasi-Newton, you don't even attempt to do that. In Quasi-Newton, you never compute the Hessian, you calculate an approximation to the Hessian. So in that sense, they are not similar. How do we guarantee quadratic rate of convergence with the Hessian modification? Okay, and related question, I think this is Omkar. It was mentioned that delta I equal to tau times I gives the minimum norm, but as the other student suggested, only negative eigenvalues changed. Will that give a smaller norm modification? Yes, it would. Okay. Right. Okay. So, how do we guarantee quadratic rate of convergence with this Hessian modification? So, this is chapter 3 of our textbook discusses this quite in detail. So, in fact, there is, theorem 3.8 of Nocedal, right? It gives you it's a theorem, again it's a tricky theorem because he himself does not give the proof. He refers you to yet another reference, right? But what he says is that if the Hessian modification No. Yeah, okay. Should be back now. Is okay? Okay. Yeah, so this theorem tells us that if the modification that I made to the Hessian each time has a bounded condition number, I still have quadratic rate of convergence. Okay, so that is what it is. But remember, all of this discussion becomes kind of unimportant for one very simple reason, and this is really the bottom line that you should take away from this class. As I approach the solution, as I come close to the solution, in fact, even this quadratic rate of convergence of the Newton method, it is in a region close to the solution where the Hessian becomes positive definite. So we don't have to worry about this. It's when I start far away from the solution is where I need to do this Hessian modification. But as I get closer, it's guaranteed to be positive definite. So all of these tricks, they don't spoil the real convergence rate. Okay, and as I mentioned, I spoke only about Hessian modification. There are other tricks in the book next to this theorem about eigenvalue modification and so on. Lots of tricks are there, which we won't discuss in detail. Okay, so alright, so as promised, now we will start talking about our a more economical alternative to the Newton method, which is the Quasi-Newton method. Okay. Okay, as I mentioned, the claim to fame of this Quasi-Newton method is that it sits somewhere between the Newton method, which was quadratic, and then I have the steepest descent or conjugate gradient method. This was linear, and Quasi-Newton sits in between. It is superlinear. Okay, so if I look at xk plus 1 minus x star, right, this is the norm that I am looking at. Okay, so as limit k tends to infinity. Right, what was the difference between superlinear and linear? Right, so this is, I can write it like this. So if it is 0, what do I call it? Superlinear. And if it is mu, where 0 mu strictly, this is linear. So slight difference between these two methods. Okay. Okay, so again, the Newton method is built on, like most things that we have studied in optimization, it's built on our Taylor's theorem. Okay. Now, if I give you, let's start with a very simple high school discussion. If I give you 2 points, a scalar function f of x, and I give you x1, x2, what is the best model that you could construct? Could you construct a quadratic? No. Best I could do is straight line. In more sophisticated language, what is a straight line called? It's an affine function, right? Affine functions means a constant plus a linear term, right? So strictly when you say a function is linear, it means it has no intercept. It goes through the origin. That's what is called, strictly speaking, a linear function. Okay, so with 2 points you could do affine. 3 points you could do quadratic. Parabola or quadratic function, right? So in the Quasi-Newton method, the idea again is that I'm going to construct models of my function at each point. Okay. Because there is the word Newton in Quasi-Newton, that model is going to be what order? Second order. That's why Quasi-Newton. Okay. So it's a little bit like this. Let us say I am here. This is my xk, and let's say this is my xk plus 1. Right. So I'm going to construct maybe like this. I should call it. Okay. Something like this. Okay, or it may even be linear. Whatever, this is some kind of a function being constructed over here. So this model is going to be called mk, okay, and the model I construct at a later point is going to be called obviously mk plus 1, okay. And Quasi-Newton is also a line search method. That means the way I go from xk to xk plus 1 is, right, That's how I go. And what will this distance be? What is the distance between xk and xk plus 1? Alpha k times pk. Right? That is our general recipe of a line search method. Alright. Now, knowing our Taylor's theorem, if I am standing at xk, okay, I want to construct a quadratic model. How would I construct this quadratic model? So, for example, at p equal to 0, this model should agree with the function. So, mk of 0, what should it be? Not xk. I am trying to model the function. So, what should it be? F of xk? F of xk has a shorthand fk. Okay. So, this is our very 0th order term. Now, I will construct a linear term and a quadratic term. Okay. So, linear term, anyone wants to guess what our linear term should be? Grad of k transpose p. Okay. And now comes the second term, which is also straightforward and easy to guess. What would it be? There has to be a half, right? P transpose. Okay, Hessian, should I put Hessian? If I put Hessian, if I commit to writing Hessian there, I am in trouble because then it becomes Newton. So, what should I write instead? Some bk, okay, which is in this case, since I am doing Quasi-Newton, it will not be Hessian, and p, right. So, this is strictly speaking just a quadratic model. The word model is very important because bk I have not specified right now. Quadratic model of f around xk, this is what it is. I take inspiration from Taylor's theorem. Taylor's theorem, only difference is bk would be the Hessian.
Do we still have the condition that p should be like somewhat arbitrary?
Yeah, in Taylor's theorem, if the larger you take p, the more terms you need to keep. So, that will always happen there. Remember, our step length alpha is there to save us in that regard. So, in that sense, p is a direction. Okay. So, before we go to xk plus 1, let us do some very simple algebra over here. What will be the gradient of m, of this mk? So, if I do this. So, remember in this expression I have written for mk, what is the variable? What is changing? P. Is p a vector or a scalar? It's a vector. Okay. So, when I write grad mk, obviously, what are my d by d of what is it? P1, P2, P3, right? P is the variable. So, what is the gradient of mk? Let us go term by term. First term, 0, constant. Second term, grad f k, okay. And what else? That half will get cancelled when I do product rule. I will be left with a bkp, okay. We made one small assumption here. What is that? Right? We assume that bk is going to be symmetric. Okay. So, let us put that in over here. Assume okay. So, let us look at, so mk of 0 is clearly f of k. Grad mk of 0 is what? Grad fk. So, you can see that mk is agreeing with fk or rather with f on two counts. It is agreeing with the function values, agreeing with the gradient value. Okay. Now, in fact, in addition to bk being symmetric in this model, since I am using a quadratic model, I should insert one more condition on it. What should that be from our entire past discussion? Positive definite, right? Assume bk is symmetric and positive definite. Okay. Okay. Now, what is the ideal P that I want? If I am at, so I am sitting here at xk, I have constructed a model and I want to know now what is the step P that I should take. So, again, without going into math, common, like if you put it into English, that we should choose that value of P such that my model MK is minimized. When is my model MK minimized? Grad M should be 0, right? So, this tells us we want grad MK at P to be equal to 0. This gives us the value for Pk, right? So, implies that Pk will therefore be equal to Vk inverse grad. I am at iteration k, I am at the point xk. Because so it's like this, I have reached a certain point in my iterations. Now I want to go further to a place where the function is minimized further, right? So I am going to say, let me restrict myself to a small neighborhood around xk, and based on what data I have about this function, I am going to construct a model. Why am I constructing a quadratic model? For the precise reason what what I just wrote over here. If I write a quadratic model, I can tell you the minimizer analytically. Well, at a point in the sense, the model is not at a point. The model is in the neighborhood. The model is constructed in the neighborhood of a point. So I am minimizing the model. I am not minimizing a point. Right? So I am let me just write that down. To minimize the model, and the model MK is valid or legitimate in the neighborhood of xk. That's why the subscript k goes with M. As I move to a new point, obviously I should construct a new model, right? This is, in very intuitive words, this is similar to the idea that if you have a very complicated function, you could keep linearizing it at each point, moving a small distance and linearizing it, right? So here we are going one step further and saying, hey, why linear? Let's do quadratic. Okay. Alright, so we've got this. Now, what was the whole argument of a Quasi-Newton method? That I don't want to compute Hessian. Hessian is expensive. Okay. So if Hessian is expensive to calculate, therefore I have replaced it by this BK. So what I would like is that this BK plus 1 should somehow come from BK. So if I have something like that, an update rule which helps me, like I have an update rule for xk plus 1. It is something, I take xk, it makes some modification, get xk plus 1. In conjugate gradient, pk plus 1 came from rk and pk, right? But you notice in the Newton method, every time I calculate the Hessian fresh, right? So people had this intuition that why not apply this kind of similar logic to the Hessian also. So this approximate Hessian, I want some update rule in order that I use all the effort I have done in the previous step to get bk plus 1. That's the sort of underlying intuition behind the Quasi-Newton model. Okay, so let's just note that the Quasi-Newton motivation okay. So the only thing that we have to worry about is, well, possibly B0 you need to spend some effort in computing, and then I keep updating. Okay. So if now let's just draw your attention to this. Okay, this is one piece of data. MK0 is FK. Similarly, if I ask you what is MK plus 1 at 0, what would it be? So I am considering XK plus 1. So this is simply going to be FK plus 1. Similarly, grad MK plus 1 of 0 would be grad of FK plus 1. Okay. So now what has happened is, I have both of these models, none of these models invoke my B, the guy that I am interested in, right. So I need to do some kind of a trick to connect these two red bubbles over here. This is the first bubble, right, and the second bubble. What is connecting these two guys is going to be some kind of a way to update B. That's the missing link between these two. Right now they look like independent models, right. So with this kind of intuition in mind, so let's note that down. This is the motivation, okay. So now let's consider mk plus 1, okay. Let's make or force this mk plus 1 model to satisfy two things. Mk plus 1, does it give me the correct gradient at xk plus 1? Let's ask question 1. Does it give me the correct value of grad f at xk plus 1? So is that a yes or a no? Yes, we saw it by construction, right? We saw this over here. It gives me the correct value of the gradient. So let's put a tick mark over here. Now let me ask you a second question. Does it give me the correct value of grad f at xk? Yes, no, or we don't know, or not necessary. It's definitely not, it's not obvious. Looking at what I have written about mk plus 1, mk plus 1, if you look at the definition of mk, if you look at, for example, over here, just replace k by k plus 1, there is no information about the previous iteration in this, right? It's all k, k, k. There's nothing about k minus 1 over here. So if I just pose the question like this, does it give me the correct value of grad f at xk? The real answer is I don't know. If I don't know, maybe there is a way for me to make it do it, and in that way I am going to get some kind of a additional constraint. I can introduce b into the picture, okay. So let's see that. Okay, so in order for us to do this, I am standing here at xk plus 1, I came from here at xk, okay. If I want my model mk plus 1 p, so let's pay attention here. I want this model to tell me something about xk. If I put p equal to 0, it is telling me at behavior at which point? Xk plus 1, right. So p equal to 0 is xk plus 1. So what is that value of p so that it corresponds to xk? I have one answer over here. Any other answer? What value of p should I put inside this mk plus 1 model so that this function tells me something about xk plus 1, xk? Minus, right, because the way I arrived from here to here was by walking a distance alpha k pk. That means if I am now already at xk plus 1, I need to walk backwards, right? Correct. Alpha k, in this case, don't worry about alpha k. Let's assume that alpha k into pk is what we are talking about over here. Right? So, this is going to be p equal to minus alpha k pk. If I substitute this inside, my model mk plus 1 will tell me about xk. Okay. So, let's look at that. And also, let's note this one thing over here. What is grad mk plus 1 p? It's nothing but grad f k plus 1 plus one more term was there. What was that? Plus bkp. So this is going to be b k plus 1 p. Okay, these are just the. So in order for me to get grad fk correct from mk plus 1, I need to substitute this value over here. So, grad mk plus 1 evaluated at minus alpha k pk. This is going to give me information about the gradient at xk, right. So, there are two ways in which I can compute this. One is just substitute into the above formula, right. So, that is going to give me grad fk plus 1 minus bk plus 1 alpha k pk, right. I am just substituting. Ideally, what should this be? This should be grad fk, okay. Right. So, this is where the choice of model or choice of B is coming into play. Because B was not specified so far, here is where the choice comes in over here, right. So, this is a critical step. Critical, you can call it a design choice. Okay. So, let us just rearrange these characters. So, you will have grad fk plus 1 minus grad, actually before that, in case for those of you who found it a little confusing, this is from the definition of grad mk plus 1, okay, and this is something we want, right. These are the two ends that we are joining together, okay. The red part follows just from the definition of grad m, the second part follows from our design choice, okay. So, now we can just rearrange these characters. So, I will have grad fk plus 1 minus grad fk is going to be equal to bk alpha k pk, looks like a row p, okay. Looks a little not very intuitive what is going on over here. So, we are going to introduce some question bk plus 1, sorry, yeah. So, this over here grad fk plus 1 minus grad fk, there is a simple notation for it that we are going to introduce. I am going to call it yk, okay. So, this is the definition of yk. So, what is yk? Difference of gradients between two iterations, okay. What is alpha k pk also known as? Can I write alpha k pk in terms of the x's? It is xk plus 1 minus xk, right. So, I am going to write this as bk plus 1 sk is equal to yk, right, because xk plus 1 minus xk is equal to sk is also equal to alpha k pk, okay. So, this is definition of sk. Okay. Now, this equation is come about by our choice. We have said I want this to be true, and this equation is important enough to get a name of its own. It is actually called the secant equation. Okay. Now, we wanted this matrix to have what property? Symmetric and positive definite, okay. How do I ensure positive definite over here? If matrix bk plus 1 is positive definite, the definition of positive definite is Z transpose AZ greater than 0 for all Z. So, in particular, is there a nice choice of vector I can stick from the left over here? SK transpose, right. So, if I left multiply by SK transpose, what do I get? SK transpose BK plus 1 SK is equal to SK transpose YK, and this should be greater than 0 for BK plus 1 positive definite, okay. This is, if this is ensured, I get, if I can somehow ensure this, my matrix B will be positive definite. So how we can ensure this, I'll come to in a short while. Okay. Now notice one thing. I've said what are the two things I wanted about BK? It should be symmetric. It should be positive definite. Now if I think of a n cross n matrix, how many unknowns are there in the n cross n matrix? N squared. If I tell you it should be symmetric, how many unknowns are there? The upper triangular, I mean one triangular part, right? So that's roughly how much? N into n plus 1 by 2, right? So BK is symmetric implies n into n plus 1 by 2 unknowns. Now n into n plus 1 by 2 is greater than n or less than n? Is greater than n, right? Now so far if you notice I have not given you enough information to determine B, because B has how many unknowns? Roughly let's say n square by 2. How many conditions am I imposing on B? The secant equation, is it one constraint or n constraints? It's actually a matrix equation, right? So it's actually n constraints. Each row of that equation is giving me one linear equation in some of the elements of B. So I have n constraints from the secant equation. Okay. So what does that mean? I don't have enough constraints. That's a good place to be in. Why is that a good place to be in? Because that means that I can do further design choices to supply the remaining missing pieces of information, and which is why you don't have one Quasi-Newton method. Again, you have a family of Quasi-Newton methods. Those are the additional constraints which people have worked out over the last maybe couple of decades, which will give you different choices to nail down the remaining, right? So remaining constraints okay. So I'll tell you, we will discuss the one very popular constraint in the literature. I'm sure many of you have probably heard of this. It's named after the inventors of this method. It's called the BFGS relation. Anyone heard of this BFGS? Okay, when you're working with the MATLAB toolbox and optimization, sometimes it will ask you for choice of optimizer. That's where you will see these different letters come up. So this is one such choice. So what is this choice? This okay, so it's a long equation to write down. I'll just write it down for sake of completeness. Okay, so notice one thing. This secant equation over here, I wrote it like this, right? So bk plus 1 sk is equal to yk. There is another way of writing it. What is bk inverse? Hessian. Remember, bk was the proxy for Hessian inverse. So you will find some equations, they work with the inverse of the Hessian. I could have as well written the equation like this, and this inverse has a special name, it's the Hessian. Okay. So this BFGS relation, what it does is, it gives us an update rule for hk plus 1 in terms of hk. It's helping us fix the other degrees of freedom. So hk plus 1 is Ah, you're right. Yeah, okay. That's when we wrote it, it was Hessian, you're right. So, anyway, what I'm saying is we can work with either BK or BK inverse. In this case, BK inverse, the symbol I'm giving is H. Okay. So, yeah, you're right, it's kind of backwards. Okay, so right, I'm not proving this. This has its own kind of proof over here, but this is, in a sense, this our Quasi-Newton method is sort of working with this update rule. Okay.